Hello, today I will show you how to implement a specific partial differential equation. I am taking the heat equation in a cookie baking process as an example, and the simulation will be performed in Mathematica. Of course, I will share you the code here in the description of the video, and the assumptions are the radial symmetry and also the constant edge temperature. So we are considering a circular cookie that is very common, and of course not a specific oven because we will just focus in the cookie. So as usually, the heat is transferring from the edge to the center of the cookie, and the mathematical model that can apply to this phenomenon is the heat equation. In particular, we are using cylindrical coordinates, and as I said, assuming radial symmetry. This equation is this one. The derivative of the temperature on the time is equal to the thermal diffusivity, and these two terms that are the second derivative of temperature on the radius plus 1 over radius multiplied by the derivative of the temperature depending on the radius. So as you can see here, the temperature in the cookie just depends on time and on the radius. So this partial differential equation is somehow easy, and well, we just need some initial and boundary conditions to solve this equation, and I will show you the code, and also I am sharing this in the description as I said. So the initial condition for this process is the initial temperature is equal to 25 Celsius degrees at time equal to 0 and for all the radius. So after that, the boundary condition is for the edge of the cookie, and at the edge of the cookie and after the initial condition, we have a temperature equal to 180 Celsius degrees. Also, in the center, we have a central condition, or the symmetry condition indeed, that is the derivative of the temperature depending on the radius is equal to 0. So the partial differential equation we are solving is this one. The initial condition is this one, the boundary condition, and the center condition is this one. So let's go ahead to the code. Okay, here we are in Mathematica. As you can see here, I am starting with the problem parameters, the thermal diffusivity, the maximum radius, the initial temperature, the external temperature, and also the simulation time. In this case, I choose 1 hour of simulation that is equal to 3,600 seconds. After that, I write the heat equation is exactly the same that I have in the presentation in the draft. And so here is the derivative depending on time, the thermal diffusivity, and the two other terms, right? I can show you, for example, to see that this is our differential equation, our partial differential equation, and here is important to mention that as temperature depends on the radius and also time, always we are writing temperature and in the bracket the radius and also the time as independent variables, right? So after that, the initial, boundary, and symmetry conditions. The initial condition is for time equal to 0 and all the radius, the initial temperature. After that, the boundary condition for the radius equal to the maximum radius is equal to the external temperature that we defined before. And the center condition is the derivative of the temperature on the radius is equal to 0. Of course, here I choose the limit for the radius when it tends to 10 up to minus 12. Yes, this is the symmetry condition. After that, we will use the NDSolve function already implemented in Mathematica. And here the way to write all these conditions and the equation is that we have to write the equation and all the other conditions that we already have. As you can see here, as you can see, I use just one equal because this, and here I use 2 This is a mathematical equality, and this is just to assign this element to this variable, right? I think it's clear enough. This is the difference between this one and this other, okay? So after that, coming back to the NDSolve function, we have to write the equation, the conditions. After that, after a comma, we have to write the temperature because this is our dependent variable. And finally, and this is a numerical solver, we have to write the interval in which the integration will be performed. In this case, the radius begins at 10 up to minus 12 until the maximum radius, and the time is between 0 and the simulation time that we defined before. The method that we're using here is the method of lines that consists that on a discretization of the spatial variable, in this case the radio, and the discretization is in this way with a tensor product grid, and also the minimum points used is equal to 200. You can also change this for getting more let's say accuracy, but I think with this value in this case is good enough. So after, you can see if you run the code until here, you will get an interpolation function that depends on the variables that we already have. Our dependent variable is the temperature, and our independent variables are radius and time. So this is the way Mathematica let us the solution, and we can use it, for example, to plot a 3D plot using the function evaluate and letting Mathematica know which is our dependent variable and the interval for the integration. This is a very common 3D plot function, and from here to the end is just to arrange some just format of the plot. So here in this plot, in this 3D plot, you can see that the radius begins here at 0 and until 0.025 meters, that is the maximum radius that we defined. And in this other axis, we have time equal to 0 until 3600 seconds. In the vertical axis, we have the temperature, of course, at the beginning. For all the radius, we are at 25 Celsius degrees, and over time it evolves. Of course, if we just look at the edge, that is the maximum radius, it changes very fast from 25 to 180 Celsius degrees. So at the edge of the cookie, it is keep this temperature, and as we go into the cookie until the center, we can see the evolution of the temperature depending on time and also on the radius. So this is the code. You can use it. I think it's very clear. And of course, if you have any question, I can help you. In addition, I use the same code. If you see, this part is exactly the same as before. And after that, I wanted to show you how to plot in a circular plot, accounting for the cookie, for the circular cookie, how the temperature evolves. And so I choose 6 different times, as you can see here, in the same range that we used before. And so I plot a 2D plot, but we have a temperature scale in color from 25 to 180 in the range that we know the temperature is. And yeah, this is the first plot at time equal to 0 seconds, after 600 seconds, and so on. And I really think this is very interesting plot because you can see how the gradient of the temperature will change over time. and at the end of the simulation all the cookie is at 180 Celsius degrees. Okay, well, in this plot our unique parameter is the thermal diffusivity, and if you want to see some different evolution of the temperature around this cookie, you can just change this one and explore any possibilities, or still fit to a specific experimental values, right? So this is all for this time. This is the solution of a partial differential equation. You can see here a very interesting 3D plot, or even a 2D plot in circular regions that can let us have a look at the gradient of the temperature. I know you find it very interesting, and see you in the next video.